So last Friday we finished section 4.3, and that was the last topic for the second exam. So this week we'll start doing review. So I'll do the review today and also Wednesday, and there's no class on Friday because that's um, the exam day. Um, if you haven't, make sure to check the email that I sent out on Friday about the second exam. Um, yeah, yeah, make sure to check that. A few did anyone say anything? Okay, so a few reminders. Um, web work 4.3 is due today. Wait, is it due today? Yeah, I think it's today. Yes, today. Second exam on Friday, and you have 3 hours to complete the exam, and it's available all day. I know that mm, most of you, many of you are in different time zones now, so make sure that when I say all day, 24 hours, I mean the Friday here in Michigan. So yeah, um, I've also posted the review checklist and then the formula sheet on Piazza. Practice exams can be found on the course website, and then there's also a sample exam on D2L. So the sample exam is showing you what are the types of questions that you would get on the real exam on Friday. It's slightly shorter than the actual exam, but I would say it's a very good representation of the exam. So make sure to check that. Basically, you only get multiple choice questions and matching questions um, in your second exam. So yeah, any questions before we start? Okay, so I only have two problems that I want to solve today. Um, they are related to first derivatives and first derivative, second derivative, and the function itself. Um, at least for the standard exams, they are those two are very typical questions that you'll see. Um, but before that, I want to do one thing that we also did last time. So I want you guys to take the next 5 minutes to go look at the review checklist. So take the next 5 minutes to go see the review checklist, and then we'll come back in 5 minutes and we'll make guesses about what questions that you should expect on Friday. So yeah, talk to you in 5 minutes. I haven't seen you in a long time, Kate. Okay. So what do you think? What do you think? What are the questions that you think will definitely show up in the second exam? Okay, critical points. That's very um, yeah, critical points, especially finding local max and local min. Well, actually, so the bigger question that you should be um, that you should be looking at is well, I guess finding local max. Okay, yeah, finding local max, local min. What else? Okay, same annotation, optimization. Okay, I'll write them in a second. So finding local max and local min. What are the other topics that are related to this too? So when we started talking about extrema, I told you that in each semester there's at least a 16-point question asking you to do graph sketching, right? So yes, so apart from finding local max and local min, you also need to know how to find intervals where the function is concave up, concave down, and so inflection points. Yeah, so derivative testing is for local max and local min. And you also need to know how to find horizontal asymptote, vertical asymptote, slant asymptote. And then sketch the graph. So these four are more like a big topic that you should know. And then someone mentioned that sigma notation. So I actually wouldn't say this is like one of the most important topics that you should know. Simply because it's usually it's very time consuming when you do questions that involve sigma notation. And then optimization, yep, that's a good one. So that's a function that has the target function. That's a problem that has target function and also the constraint, right? Related rates. Wait, do we have this on the first exam? Do we have this in the first exam? I think we did. Yeah, I think this was the first exam. Yeah, this was the first exam. Mm-hmm. Okay, what else? Yep. So you should see the second exam as like there are two main topics that you should focus on. The first part is a derivative. So first derivative, second derivative, and then the second topic is the antiderivative or integration. Okay. And then, yep, linearization. Um, so I want to confuse you by also adding the topic Newton's method. There's one question on the no, not second exam. On the sample exam, I think it was the first question. Um, that's asking you what is the difference between linearization and Newton's method. So that's something. This is like a comparison that you should do on your own. What else? Yep, I already did that in here. So horizontal asymptote, vertical asymptote, and slant asymptote. What else? Summations, that's the same as sigma notations. Ooh, mean value theorem. Okay, yeah. Okay. Um, yeah, maybe I should add the fundamental theorem of calculus to the antiderivatives here, because that's like I mean, it's called a fundamental theorem of calculus, so that's something you should definitely look at. Okay. Anything else? No? Okay. Um, yeah. So any other questions and any questions in general that you want to ask me before I start doing? No? Okay. Let's see which one. This one. Okay, so this is the, which one is it? This is the second exam in spring semester. And then let's look at question 17. Okay, so you're given the graph of the first derivative, and then the first question is asking you what are the critical points, and which one is local max, which one is local min. And then second part of the question says find out all the inflection points, and then the final question, sketch the graph of f of x. So you're given the first derivative graph. How do I find critical points? How do I find local max, local min? So what's the definition of critical points again? When you set the derivative to be 0, so it's either the derivative is 0 or undefined. So you need to look at the first derivative and find out where's the 0 and where's the undefined. It doesn't have any undefined points because as you can see, the graph of f prime is pretty nice, so it doesn't have any undefined points. And so where's the 0? So where's the first derivative is 0? So x equals a and d. So those are the only two critical points. Now, which one is the local max? Which one is the local min? Okay, a is a local min. No, a is a local max. So let's see why this is correct. So you can see from the graph that to the left of a, the derivative is positive, right? Above x. To the right of a, the derivative is negative. So if the derivative is going from positive 0 to negative, that means x equals a is a local max. And let's check x equals d. So to the left of d, the derivative is negative because that's below x. To the right, it's positive. So if the derivative goes from negative 0 and then positive, then it's a local min. Make sense? Questions? All right, so that's just the first part. Second part, find other inflection points of f of x. So this is part A. Any ideas? Yeah, for finding inflection points. Usually you would look at the second derivative and then you set it to be 0 or undefined. But we don't have the second derivative here. We don't even have the function itself. So what do we do? So what's the definition of inflection points again? Okay, so you look at the points where the graph changes the concavity. Means the derivative either goes from positive to negative or negative to positive. And it also means that the second derivative has to be 0, or it could also be undefined. And here's a fact. So forget about the undefined. So in most cases, for good enough function, and by good, you can imagine there's some technical assumptions like differentiable, continuous, and stuff. Well, actually, differentiable would be enough. So for good functions, x equals a is an inflection point. That's the same as saying that x equals a is a local max. Okay, I should write this properly. So x equals a is an inflection point for the original function f of x. That's the same as saying x equals a is a local max or min for the first derivative. One way to see this is inflection points necessarily the points where the second derivative is 0. And so, and then to the left and to the right, the second derivative must have different signs. But second derivative equals 0 tells you that it has horizontal asymptote on the first derivative graph, right? And so it means that it has to be a local max and local min. Does it make sense? Now, using this fact, can someone tell me what are the inflection points? No, I'm saying no. So I'm saying that you have to look at f prime and find out what is the local max and local min on f prime. So what are the local max and local min on f prime? Okay, so I'm talking about f prime and I'm not talking about the original function. Let me say this again. I'm saying that to find the inflection point for the original function, other than the usual way that we did, the other way is to look at the first derivative and find out where is the local max and where is the local min on the derivative. So we have to check the peak points on the derivative, the lowest and highest points on the derivative. And so the lowest point on the derivative is here, b. The highest point is e. And those are the inflection points for the original function. Questions? No? Okay. Okay. So do you understand do you understand the fact that I just mentioned? Okay. So I'm saying that to find an inflection point for the original function, you just need to look at the first derivative and find out where is the local max and where is the local min on the derivative, right? That's a fact that I just put down, right? And so part B is about finding the inflection points for the original function. And you're already given the graph of the first derivative. And I know that the local min on the first derivative happens when x equals b, because that's the lowest point. And the local max on the first derivative happens when x equals e, because that's just the highest point. And so those are the points, those are the inflection points for the original function f of x. Yes. Um, so I'm not saying that this is a very straightforward fact, but that's something you can think about. I imagine there's only 5 people that actually understood this, but this is something you definitely want to spend time on and think about this. If you have any questions about this, let me know. Um, okay, let's move on to the next part. So part C, true or false, f of b is bigger than f of d. So the function value at b is bigger than the function value at d. This is something that I need to think about. Yeah, true or false? False. Why is it? Why is it? Why is it false? No, it's not a local min for the original function. It's the local min for f prime. That's different. Wouldn't e not be an inflection point? Because Okay, so talking about part B. So Ryan, you say that E is not an inflection point because there isn't a max or min on the right side. What do you mean? I don't actually understand. Okay, so back to part B. Okay, so what is part B? Part B is asking for inflection points for the original function. And then the fact that I just put down here on the screen, it says that I only need to look at the first derivative and find out what is the local max and what is the local min on the derivative. So I need to look at the peak point and the lowest point, the highest point and the lowest point. And obviously from the graph, you can see that the highest point is when x equals e, and the lowest point is when x equals b. And so those are the only two inflection points for the original function. Does that answer your question, Ryan? Yep. Back to part C. Again, part C is about the function value f of b and f of d. It's the original function, not the derivative. So you cannot say that b is a local min for the original function because it's not. It's actually an inflection point. So so maybe look at the interval from b to b to d. So on the interval from b to d, is the function increasing or decreasing, and why? I'm asking for the original function f of x. I'm not asking about the function f prime of x. So from b to d, is the function f of x increasing or decreasing? It's decreasing. Why? Yep, exactly. So from b to d, you can see that the derivative is below x. So it's less than 0. That means f of x is decreasing on this interval from b to d. So which one has the higher function value, b or d? So if a function is decreasing on b to d, which one has the higher value? Is it b or is it d? It's decreasing, right? B. Yeah. If a function is decreasing from b to d, the further you go, the lower function value you will get. Make sense? So this is actually true. It's true that f of b is bigger than f of d. Questions? Okay. Part D. Okay, think about what does it mean by saying that a function is decreasing? It means that the further you go, the lower function value you will get. So the function value at b would be the highest, and then it goes down and down as you get closer and closer to d. Make sense? And you can actually see that from part A as well. You found that d is a local min. So yeah, it's a local min. Any other questions? All right, part D. Sketch the graph of f of x given that f of 0 is 1. So when x equals 0, let's say that it's 1. So the initial point is here. Okay, now what do we do? Um, so to remind you, local max is at, wait, where's the local max again? Local max x equals 8. Local min x equals d. Inflection points x equals b and e. It goes up to a. Yep, so it goes up to a. So between 0 and a, I know that it's increasing, right? Because x equals a is a local max. But is it like this? Or is it like this? So I have two options. First option is this one. Second option is this one. Okay, someone's saying that it's the first one, and why is it? Why? What is positive? Okay, cool. So can someone tell me what is the difference between orange and red? What is the difference between first one and second one? Let me draw this properly. So this is the first one, and this is the second one. They are both increasing. The only difference is one is opening downward, the other one is opening upward. And how do I know which one is correct? I know it's going up, but you can see both orange and red, they are both going up. But how do I know which one is the correct one? Oh God. Okay. So from the graph of f prime, would you be able to tell when is the second derivative positive or negative? Yeah. Okay, so Ryan is correct. So it should be orange, and the way you see it is we know that it's a local max. And so the only thing I need to figure out is whether it's concave up or down from 0 to a. So if you look at the graph of f of prime from 0 to a, the second derivative would be the slope of the first derivative. What is the slope of the derivative when, what is the slope of the first derivative from 0 to a? Is it positive or negative? So from 0 to a, if you look at the graph of f prime, the second derivative should be negative because the slope of the first derivative of from 0 to a is negative. Does it make sense? So it's actually concave down. Okay. Let's continue. And then I know that B is an inflection point. So from 0 to a, if it looks like this, then it should also look like this. And then at some point, it has to change the concavity. So at B, it has to change the concavity. So it's only concave down from 0 to B. Make sense? And now we can continue the graph from B to D. I know that D is a local min. And using the same logic, D should look like this. Is it okay? So around D, it should be a U shape opening upward. And then I also know that the point E is an inflection point. So the opening upward has to stop at x equals E. And after the E, it has to become concave down. Questions? So this is local max. Inflection point. Local min. Inflection point. Can B also be 0? Do you mean the function value? Yes. This is only a rough sketch. If you like, you can draw the function value at B to be 0, but it doesn't matter. The only thing that matters is that it's just the shape of the graph. So it has to look like this. Questions? Okay. Let's move on to the next one. By the way, if I'm confusing you, that's a good thing. I guess the only thing I can say is go back to see our notes and then watch this video again and see if you understand. Okay, so this is the fall semester 19. Again, second exam, question 6. So given the function, the first derivative and the second derivative, and then you're asked to find the domain, vertical asymptote, horizontal asymptote, slant asymptote, find out where is it increasing, decreasing. And and find out local max and local min, find concave up, concave down, and then finally sketch the graph. So this is a 16-point question that I talk about. So first part, what is the domain of the function? So the original function was x squared divided by x minus 1. What is the domain of the function? Can I put in negative numbers? Okay, so everything except 1. So negative infinity to 1, union 1 to infinity. Part B, vertical asymptote, horizontal asymptote, and slant asymptote. So let's find out what is a vertical asymptote. How do I find vertical asymptote? Yep, so vertical asymptote, you just need to look at the denominator. X equals 1 makes the bottom 0. So x equals 1 is a vertical asymptote. And that's the only vertical asymptote. Horizontal asymptote. So how do I find horizontal asymptote? So what do we need to compute? Okay, yeah. So need to compute these two limits. When x goes to positive infinity and when x goes to negative infinity. And you only need to look at the highest degree terms. So x squared divided by x. Oops. And the same for the second. So for the first one, if you divide by x, you get x. So when x goes to infinity, this one is infinity. When x goes to negative infinity, this one is negative infinity. So no horizontal asymptote. Questions? Okay, let me finish up the slant asymptote before I let you go. So slant asymptote. How do I find slant asymptote? Okay, you divide. You do the long division. So x multiplied by x, you get x squared. X times -1 is negative x. You subtract. So this is x plus 1, x minus 1. Subtract again. This is 1. Yeah. So whatever you got here is a slant asymptote. Is D slant asymptote. Is it okay? Any questions? Okay, so I'll continue this example on Wednesday, and if you have any topics that you want me to go over again, let me know, and then I will do it on Wednesday. Any questions? All right. You're free to leave if you have no questions. Otherwise, I will stay for a minute if you have any questions.